In 4.3, we're going to continue on with some more properties of polynomials. Now remember, the goal here basically is to be able to factor our polynomials so that we can locate the zeros. This first theorem we're going to look at is what we call the conjugate zeros theorem. And all it says is that if a plus bi is a zero of our polynomial, then the conjugate a minus bi will also be a zero. So conjugate zeros come in pairs where you have the plus and the minus. In example 1, it says to find a cubic polynomial having zeros -1 and 3 minus I. Well, if 3 minus I is a zero, by the previous theorem, 3 plus I must also be a zero. So I have these three zeros, and this is a cubic polynomial. That means degree 3. So since the degree is 3, I can have at most 3 zeros, and I have them. So that's all my zeros. I can use this information in part A to write p of x equal to, so now if -1 is a zero, then x minus -1, which is x plus 1, will be a factor. If 3 minus I is a zero, then x minus parentheses 3 minus I will also be a zero, as well as x minus parentheses 3 plus I. I'm going to clean this up and get rid of the inner parentheses to write x minus 3 plus I, x minus 3 minus I. And then we'll go ahead and play around with these last two. Because there's an I there, I really need to multiply it out and try to get rid of the I. So I'm not looking forward to this multiplication, but let's go ahead and distribute that first term x over the that last set of parentheses to get x squared. So I'm going to ignore the x plus 1 for now. X squared minus 3x minus xi. And then distributing the -3, I get a minus 3x plus 9 plus 3i. Distributing that plus I get a plus xi minus 3i minus I squared. So I have an x squared. I don't see any other squares, so that would give me the x squared. If I look at the minus 3x, I have another minus 3x, which would give me the minus 6x. Now I have a minus xi and a plus xi, so those will cancel. I have a plus 3i and a minus 3i, those will cancel. Also keep in mind that I squared is -1, so that's going to be a minus -1 or a plus 1. So we have a plus 9 and a plus 1 would give me a plus 10. And then now I'm going to add in that x plus 1. Here's my polynomial. And of course, we need to also multiply that out and get rid of our parentheses. I get x to the third minus 6x squared plus 10x. And then distributing that 1 plus x squared minus 6x plus 10. Combining my like terms, I'll get x to the third minus 5x squared plus 4x plus 10. And notice that this polynomial is degree 3, so it is a cubic polynomial, which tells me in all likelihood I did my math correctly, but there can always be error. Now the second part of this, part B, says find a polynomial satisfying part A. So we already found that polynomial. But in this case, we're going to have this special condition that p of 1 is equal to 5. Okay, so let's think about that. We need p of 1 equal to 5. So I'm just going to put in 1 for x in the polynomial I have above, and I'll get p of 1 is equal to 1 minus 5 plus 4 plus 10. Ooh. Okay, so it looks like I am getting 10. So I don't have p of 1 equal to 5. So I need to find some number. I'm going to call it a, so that when I multiply p of 1 by this number a, I get 5. Well, p of 1 is 10. So if I simply divide both sides by 10, I get a is equal to 5 over 10, or in other words, a is equal to 1/2. That means that the polynomial that will satisfy p of 1 is equal to 5 would be 1/2 times the polynomial I had in part A, which is the x to the third, minus 5x squared plus 4x plus 10. And of course, we're not going to leave it like that. We have to distribute that 1/2 to get the final polynomial, which is going to be 1/2 x to the third minus 5/2 x squared plus 2x plus 5. We can double check and make sure that this is correct by computing p of 1 and see if we get 5. So that would be 1/2 minus 5/2 plus 2 plus 5. And yeah, that's going to be equal to 5. So this checks out. Well, let's go ahead and kind of see where we're at so far. In example 2, it says to sketch the graph of this polynomial. And notice that this polynomial is already factored. So remember, these factors that we have here, those would be our zeros, which would be our x-intercepts. So very important points to have if you want to graph. But remember from our prior section, we also can find our end behavior. So what we're going to do is we're going to find the end behavior. We're going to plot our zeros, and then we're going to see if we need some additional points. Now, this is only a sketch, a rough sketch. It's not going to be perfect. You can always check using a graphing calculator or a graphing device such as Desmos. So the end behavior, remember what we're looking at. We're looking at degree, and in this case, it's 3, which is odd. And then we're looking at the leading coefficient to see if it's positive or negative. Our leading coefficient is 2, so it's positive. So since I have odd positive, I know what my end behavior is going to look like. It's going to look like that. It's going to go from negative to positive infinity. So I'm going to put that together with my zeros. This is already factored, so the x minus 2 gives me a 0 of 2. 2x plus 3, just set it equal to 0, and you'll get x is equal to negative 3 over 2. X plus 1 gives me a 0 of negative 1. I'm going to go ahead and plot those zeros on my graph. Let's see, 1, 2, 1, 2. We have one at 2 and one at negative 1. So here we have 2, negative 1, negative 2. One between negative 1, negative 2, so this would be the negative 3/2. Well, those zeros are very close together. Now think about the end behavior. We have a positive infinity, and then down here we have a negative infinity. So looking at the zeros and the end behavior, I have no choice. My negative 3/2, that's my last 0. I have no choice but to go down from there, following that end behavior. And then when I look at the 2, I have no choice here but to go up and follow that end behavior. Now this graph is going to look kind of weird. What happens between the -3/2 and the 1? Well, remember, polynomials are nice smooth curves. The only choice I have, the only choice I have is to come up and go down. And then between the -1 and 2, the only choice I have is to do something like this. Now this is just a rough sketch. I really don't know how far down from -1 to 2 the graph will go. I know between the -3/2 and the -1, there's not much room, so I don't have much leeway there. But it is possible if I put in some additional points, and I'm not going to spend too much time on this, because again, it's just a sketch, that I can get a better drawing of this graph. So let's say I wanted to look at x equal to 0. I don't have that point. Oh, and that's the y-intercept as well. So if x is equal to 0, then my y value is going to be -6. So let's just say this is -6. Let's try 1. If x is equal to 1, then my y value is going to be 2 plus 1 minus 7 minus 6. I think that is going to be -10. So maybe this will be a -10. And I could see that this graph is going to come down a little bit more. My sketch is going to be a little bit different now. I got to kind of go down and then come up. So you can use a graphing program to double check, but this is basically the idea. Again, I know this looks really gross, but this is just the basic idea. Using end behavior and the zeros, we can get a rough sketch of our graph. So what we want to do is we want to be sure to label all the points that we found. Since it's kind of an ugly graph, we want to make sure it's going through the correct points. This was 0, -10. Oh no, this wasn't 0, sorry. This was 1, -10. And here we have 0, -6, -1, 0, -3/2, 0. So that's the basic idea. But let's say, going back to our polynomial, let's say that we didn't have it already factored for us. Factoring polynomials can be very difficult. We could use synthetic division, and if we have a 0 remainder, we know we have a factor. But think about this. If I didn't see those factors there and I just saw this polynomial, what would I choose to divide by? There's an infinite number of choices in numbers that could be possible zeros. That's going to bring us to this rational zeros theorem. So the rational zero theorem will help us to kind of focus our attention on numbers that could work. What the rational zero theorem says is that if you have this polynomial, and here the constant term, the a sub 0, it can't be equal to 0. So let's just pause a little bit. Let's just say I have a polynomial like p of x equal to, I'll just do something simple like 3x to the third minus 4x. So notice that there's no constant term, no a sub 0. If that is the case, then you can always factor out an x to get 3x squared minus 4. So the polynomial that you're going to look at, your p of x, will be what's inside the parentheses, because that x on the outside is already a 0. We've already factored that out. So we're only concerned with breaking down what's left over. And in that case, that polynomial does have a constant term that's not 0. Let's go back to this theorem. If we have a polynomial and constant terms not 0, then rational numbers of the form p of q could be possible zeros of our polynomial, provided that we look at all the factors of our constant term a sub 0 and all the factors of our leading coefficient a sub n. So we're going to be looking at the a sub 0 and the a sub n, and all the numbers that can divide those, all their factors. And then those would give us our possible rational zeros, where the a sub n, the factors of your a sub n, that would be this p, so that would go on top, and the factors of a sub n, that would be the q, so that would go on the bottom. It's probably easiest if we just look at example 3 and list all the possible rational zeros of here p of x is equal to 8x to the 4th plus 3x to the 3rd minus 7x plus 6. So first of all, note that my a sub 0 is equal to 6. And if I was going to list all the possible factors or numbers that divide 6, well, 1 divides 6, but so does negative 1. So plus and minus 1, those are factors. 2 divides 6, but so does negative 2. So plus and minus 2, as well as 3, so plus and minus 3, and 6 divides 6, but so does negative 6. So those are all the possible factors of our constant term 6. Now our a sub n, that's 8. If I were to list all the factors there, plus minus 1, plus minus 2, plus minus 4, plus minus 8. So if we have to list our p over q, so remember the p goes with your a sub 0, q goes with your a sub n. So the factors of the constant term are on the top. It would be plus minus 1, plus minus 2, plus minus 3, plus minus 6 over plus minus 1, plus minus 2, plus minus 4, plus minus 8. So let's look at all the possible combinations. If you look at the plus and minus 1 over plus and minus 1, 1 over 1 is 1, but it's going to be plus or minus 1. Look at the plus and minus 1 over plus and minus 2. That's 1/2, so plus minus 1/2. Plus and minus 1 over plus and minus 4 will give us plus minus 1/4. And then the plus minus 1 over the plus minus 8, plus minus 1 over 8. And we'll do the same thing with the 2 in the numerator. So 2 over 1 would be plus minus 2. 2 over 2 would be a plus minus 1, which is already listed. 2 over 4 would be plus minus half, which is already listed. And 2 over 8 would be 1/4, so that's already listed. We'll go to 3 over 1. That will give us a plus minus 3. Then 3 over 2 plus minus 3/2. 3 over 4 plus minus 3/4. 3 over 8 plus minus 3/8. Go to the 6. 6 over 1, so we have plus minus 6. 6 over 2 would be plus and minus 3, which we have listed. 6 over 4, so that would be 3/2 listed. 6 over 8 is 3/4, which is listed. So down below here, oh my gosh, we have so many. These are all our possible rational zeros for this polynomial. So if I were to use synthetic division to find the zeros, well, first of all, I hate working with fractions. So I would start with maybe the plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. If those don't work, then I'm stuck. I have to try the fractions. But there will not be any other rational zeros except for ones that are listed here. So that's nice. At least we have a starting point when we check our zeros and try to factor our polynomials. Now I'm just going to mention these last two theorems. We're really not going to do much with it. So we have these two theorems. The fundamental theorem of algebra, all that says is that a polynomial that has degree 1 or more has at least one complex zero. And here when we say complex zero, they're also including real zeros. So you could think of it as just 1, 0. And then this number of zeros theorem says that if you have a polynomial of degree n, it has at most n distinct complex zeros. So again, complex includes real. Putting those together, all those theorems are saying is that if the degree is n, there are n zeros. But these n zeros can be complex with imaginary, such as an a plus bi, can be zero, or can be real, sorry, but they can also be, notice in this second theorem where it talks about distinct or different, that means they can also be the same. So for instance, you could have x minus 2 as factors or these zeros of a polynomial. So you could have duplicate or multiple copies of a zero. You could have complex zeros. You could have real zeros. But the amount of zeros matches the degree. So we're going to talk about this idea of having the same zero. We call that the multiplicity of zeros. It kind of follows n behavior in a way. So if you look at a multiplicity of 1, so let's just say that 2 is a 0. And I only have one of those. So that means at this point 2, it's going to cleanly go through the x-axis. Remember, these are x-intercepts. And it's either going to go down or it's going to go up, but it's going to pass through the x-axis cleanly. What if our multiplicity is even? Well, let's just say we had -2 and -2. We had 2 of these. Then the behavior at that -2, that x-intercept, is either going to be it just touches and goes up, or it goes down. So this looks like little parabolas, and it should, because when we think even, think about n behavior. Whenever you have an even degree, both ends go up or both ends go down. If you have an odd multiplicity, so let's just say we had 3, 3, and 3 of these. Then the behavior at that point is going to, look at this squiggly line. It's either going to look like an S or a flipped over S. And those are our only choices. In example 4, we want to find a polynomial with 0, 0 of multiplicity 3, a 0 of 3 with multiplicity 1, and a 0 of -I. So let's just look at what this means. We have a 0 of 0, and its multiplicity is 3. So remember, when we factor, it's always x minus the 0. In this case, it is 0. But we have 3 of those. And then we have a 0 of 3, multiplicity of 1. So that's going to be x minus 3. But I only have one of those. And then I have a 0 of -I. But because I have -I, I'm also going to have positive I, which gives me x minus a -I would be x plus I. And then I have x minus I. Got one of each of those. So when I look at all of these exponents, I have 3 plus 1 plus 1 plus 1, It looks like I'm going to have a polynomial of degree 6 because I have 6 zeros. Some of them are the same, like the x minus 0. I got 3 of those, and some of them are complex, but if we total them all up, there's 6. Part A, we're supposed to find this polynomial. And I already know that the x minus 0, I got 3 of those. I'm not going to write x minus 0. I'm just going to write x to the third. Simplify it, right? And the x minus 3, I have 1 of those. And then I have an x plus I and an x minus I. And that is a polynomial that has all those given zeros. I'm going to multiply out especially the x plus I, x minus I. And in fact, I'm going to distribute the x to the third to get x to the fourth minus 3x to the third. And then when I multiply the x plus I, x minus I, it's going to be x squared minus an I squared will turn into a plus 1. And then distributing the x to the fourth, I get x to the 6th plus x to the 4th, then minus 3x to the 5th, minus 3x to the 3rd. I'm going to write this in descending order, highest exponent to smallest. And this is my polynomial that has those given zeros. Notice that this polynomial is degree 6, which is what I expected. Now we're going to try to graph this polynomial. So that would be our part A, or B, sorry. First thing, end behavior. My polynomial is an even degree, it's 6. Leading coefficient is 1, which is positive. So even positive means that I'm going to have this type of end behavior where they both go up. I have my zeros. The ones that I'm going to graph would be the 0 and the 3. Plus and minus I, those are imaginary numbers. They cannot be graphed in our real XY plane that only contains real numbers, does not contain imaginary numbers. So we actually only have 2 zeros. Let's go ahead and graph the zeros. On this graph, we have a 0, 1, 2, 3. And we know our end behavior, both ends are going to go up. The next thing I want to do is I want to look at the multiplicity, because although I have only 1, 3, so I know that we're going to pass cleanly through, and I know it's going to go up because it's got to match with my end behavior. It can't go the other way, or else it would not match with the end behavior. Let me get rid of that. So I know it's going to pass cleanly through. But the 0, remember there's 3 of those. So I have a choice. It's either going to look like an S. I don't think that'll work, because look at the end behavior. Eventually it's going to have to come back over the x-axis to match the end behavior, and I don't have a 0 there. I found all the zeros. So it won't be that choice for the multiplicity. It'll be flipped. So something like this. Okay, and now I can see that if I were to connect these and keep going up, I could get this graph. But let's go ahead and find some more points just to double check. Additional points, maybe, let's see, we already have x equal to 0. but we haven't tried 1. What if x is equal to 1? Then y is going to be 1 minus 3 plus 1 minus 3, which is negative 4. Okay, so at 1 we have negative 4, 1, 2, 3, 4. Oh, interesting. So I'm going to have to adjust my 0 there to be sort of down like this. Why don't we try 2? Oh, maybe not. Maybe I just want this one. So again, it's just a sketch. So this sketch that I have here is pretty close, I guess, if we checked in Desmos to what it should be. Points would be 3, 0, 1, negative 4, passes through 0, 0, and that's it. So typically, once you have the end behavior, the zeros, the multiplicity, then you just find additional points kind of near the zeros so you can get a better idea of the graph. But this is good enough because remember, we're just looking at a sketch. The last thing we're going to do in this section is we're going to talk about this boundedness theorem. What the boundedness theorem allows us to do is further reduce the amount of choices of maybe the rational zeros, because you know that list was kind of long. So if we can find a highest value and a lowest value, so that all of our zeros fall between those two values or are bounded by those two values, then maybe we can reduce the number of choices we have with our rational zeros. Our boundedness theorem says that you have a polynomial. Now here we need a positive leading, oops, I don't want that. We need a positive leading coefficient. So if you don't have a positive leading coefficient, just factor out a negative, and then whatever's left over in parentheses, that would be the polynomial you're working with. So let's say that we're going to do synthetic division by some x minus c. If that c value is greater than 0, so it's positive, and you look at the synthetic division, look at that bottom row, that very last row. If those entries are all non-negative, so none of them are negative, then you will not have a 0 greater than that c value. So that would be what we call an upper bound. So no zeros greater than c. So c is going to bound them. If c is negative, and when you do synthetic division, the bottom row alternates in sign. So negative, positive, or positive, negative. And here, if you get a 0 in the bottom row, you can choose it to be either positive or negative. Then that tells you that there's not going to be any zeros for your polynomial that are less than c. So c is what we call a lower bound because you can't have a 0 lower than that. So putting bounds on our choices. Example 5, we have this polynomial 2x to the third plus x squared minus 13x plus 6. And it says list all the possible rational zeros of p of x. Again, we're going to go back to that, I want blue, sorry. We're going to go back to the rational zero theorem. Our a sub 0 is 6. So all the factors of 6, that would be our p. All the factors of 6 would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And on the bottom, we're going to look at all the factors of the leading coefficient 2, which would be plus and minus 1, plus and minus 2. So if we look at all possibilities, let's look at the 1 first. 1 over 1 is plus or minus 1. 1 over 2 is plus or minus 1/2. Look at the 2 in the numerator. 2 over 1 plus or minus 2. 2 over 2 is plus or minus 1, but we already have that. Then we're at the 3, which would give us a plus minus 3. And then a plus or minus 3 over 2, or 3/2. 6 over 1 would give us a plus or minus 6. And then 6 over 2 gives us a plus or minus 3, which we already have. So these are our possible rational zeros. We have 2, 4, 6, 8, 10, 12 choices. And half of them, I guess, or, well, not, actually most of them are nice numbers, 1, 2, 3, and 6. So not so bad. We're going to now use this boundedness theorem in part B to show that there is no zero greater than 3, which means I'm going to do synthetic division, and I'm going to look at the bottom row to see if they're all non-negative. So our coefficients would be 2, 1, negative 13, and 6. When I do my synthetic division, I leave a space, bring down the first number 2. 3 times 2 is 6, add to get 7. 3 times 7 is 21, add to get 8. 3 times 8 is 24, add to get 32. So notice that this is non-negative, and that tells us that 3 is an upper bound. So we've just shown that there is no zero higher than 3, which is nice because we can take away that positive 6 in our list of rational zeros. In part C, we're supposed to show that there is no zero less than negative 4. So I'm going to take negative 4, complete my synthetic division, which is 2, 1, negative 13, and 6. Leave my space, bring down the 2, multiply, negative 4 times 2 is negative 8, add to get negative 7. So far so good, it's alternating. Negative 4 times negative 7 is a positive 28. I'm going to add to get 15. Negative 4 times 15 would be a negative 60. Add to get a negative 54. I hope I did my math correctly. So notice we have alternating. And that tells us that negative 4 is a lower bound. So we will not have a rational zero smaller than negative 4, which means we can also, in our rational zero choices, take off the negative 6 as well. So we've reduced our choices a little bit. Let's look at part D. Part D says to find all the zeros of p of x and write the polynomial in factored form. So going back to our choices of our rational zeros in part A, because of our upper bound being a 3 and our lower bound being a negative 4, we can take out the plus or minus 6 from our choices. So what we're going to do now to find the zeros is use synthetic division. If we get a zero remainder, that value is a 0. But I don't like fractions, so I'm going to actually start with positive 1. And if that doesn't work, I'm going to go to negative 1. If that doesn't work, I'm going to go to positive 2 and negative 2. My last choices will always be my fractions because I don't like to do fractions in synthetic division. Okay, so bring down the 2. 2 times 1 is 2. Add them, I get 3. 3 times 1 is 3. And I can already see that this is not going to work. Negative 10 plus 6 is a negative 4. Remainder needs to be 0 for it to be a 0. So the 1 didn't work. What about negative 1? So 2, 1, negative 13, 6, space, bring down the 2. Negative 1 times 2 is negative 2. Add to get negative 1. Multiply. Add. No, this is not going to work. All right, so back to the rational zeros. I'm going to go to the positive and negative 2. So if I do a positive 2, 2, 1, negative 13, and 6, I hope it's not a fraction. 2 times 2, that's 4. Add to get 5. 2 times 5 is 10. Add to get negative 3. Ah, here we go. Negative 6. We have our 0 remainder. That tells me that 2 is a 0. And moreover, once I factor with that 2, the 2, 5, and negative 3 will be the remaining factor when I factor my polynomial. So this polynomial, p of x, is going to have a factor x minus 2. And the remainder will be the 2x squared minus 5x minus 3. Now I could continue to use synthetic division on the 2x squared minus 5x minus 3, but I'm pretty sure that this factors. This would be 2x and x. If I take 2 times 3, that gives me a 6. And it's a, oh, I'm sorry, this should have been a plus 5x. So that should be a plus and a minus. That will give me 2x squared plus 6 minus 1 gives me a plus 5x. And then I get the minus 3. And this is completely factored. Now I could have added to go ahead and graph this polynomial, but I think we've done enough graphing in this section. I just wanted to make sure that we understood how to use all these theorems and how helpful it can be when you're trying to factor polynomials. So that is it for this section.